Hi, in this video I will be showing you problem number 9 of chapter 16 section 4. Use Green's theorem to evaluate the line integral along the given positively oriented curve. Integral over c y cube dx minus x cube dy, where c is a circle, x square plus y square equal to 4. So we are asked to apply Green's theorem to evaluate the line integral. The curve C is given to be positively oriented, which is a requirement for Green's theorem. So let's see what Green's theorem is. If C is positively oriented, piecewise smooth, simple closed curve in the plane, and D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then integral over C P dx plus Q dy equal to double integral over D, dou Q by dou x minus dou P by dou y, partial derivative of Q with respect to x minus partial derivative of P with respect to y dA. Where F is Pi plus Qj, and the line integral over C f dot dr also means integral over C P dx plus Q dy. Now let's consider the line integral given, which is integral over C y cube dx minus x cube dy, which is integral over C P dx plus Q dy. So we can determine what P and Q are. P is y cube and Q is negative x cube. We can also take the derivatives of P with respect to y and derivative of Q with respect to x. They are 3y square and negative 3x square respectively. Now integral over C y cube dx minus x cube dy equal to double integral over D dou Q by dou x, which is negative 3x square, minus dou P by dou y. So we are using this formula over here. So it is dou Q by dou x would be this. Dou P by dou y would be negative 3y square. Substituting them into that formula, we get double integral over D negative 3x square minus 3y square dA. So this is by Green's theorem. Now integral over C y cube dx minus x cube dy equal to, we have to evaluate this double integral, just negative 3 times x square plus y square in parenthesis dA. Now as D is the domain, which is a disk, x square plus y squared. So C is a circle and circle bounds a disk, x square plus y square less than or equal to 4. So where D is the disk, is the domain, bounded by the circle with center at the origin and radius 2, x square plus y square equal to 4. C is a circle with center at the origin and radius equal to 2. Now, if we look at the domain one more time from the earlier picture, so it's negative 2 to 2. The circle C is a circle with center at the origin and radius 2, and it bounds a domain D, which is a disk, which is the interior of the circle. Now domain D can be written as all those xy such that negative 2 less than or equal to x less than or equal to 2, and for y it is negative square root of 4 minus x square to positive square root of 4 minus x square. But in order to use Green's theorem, it will be easy for us to use the polar coordinates for the domain D, because D is bounded by the circle. So whenever the domain is a disk, the easy substitution would be the polar coordinates. So it's r comma theta, where r lies between 0 and 2 and theta lies between 0 and 2 pi. From the previous step A that we got, integral over c y cube dx minus x cube dy equal to double integral over d negative 3 times x square plus y square dA, which when converted to polar will give us negative 3 double integral integral 0 to 2 pi, then r varying from 0 to 2, negative 3 times r square, then dA will change to r dr d theta in polar coordinates. Now, we can write this as negative 3 times integral 0 to 2 pi d theta. We can separate r and theta because they are all definite limits. So integral 0 to 2 r cube dr, which is negative 3 times 2 pi times r to the power 4 over 4 between 0 and 2. So computing this, we get negative 6 pi times 16 over 4, which is negative 24 pi. So that is the value of the line integral. So in this problem, notice that the curve given is already given to be positively oriented, so we can directly apply Green's theorem. If it is not, then we have to make adjustments to the way we evaluate the integral. Hope this video helps.